Hi, thanks for coming in my presentation. In this talk, I'd like to add a new perspective that silent feature contributes to automatic dimensional speech emotion recognition. My name is Bagus, and this paper was written by me and Masato Akagi. We are from JAIS, Japan. Let me begin my presentation by outlining the contents. This is how I will be proceeding today, focusing on the effect of acoustic feature with and without silent feature, including the observation of different threshold factors in silent pause feature calculation. So let's move to the introduction. Silence or silent pause is a cue for human emotion perception. We, human beings, can guess the emotion of the speaker indicated by their pause in speech. For example, in high arousal emotion like happy and angry, people tend to use fewer silence. For a computer, it is not clear whether silence is useful. This emotion feature may be useful for automatic speech emotion recognition by computer. We propose to count silent pause frames as a feature to improve dimensional speech emotion recognition. So what's dimensional speech emotion recognition? Although categorical emotion is more common in everyday life, dimensional speech emotion is argued scientifically share more common on different people than the categorical emotion. Russo and Mehrabian proposed three-dimensional emotion including valence, arousal, and dominance, the VAD model. Valence related to negative or positive the emotion is. Arousal related to the degree of activation from sleepy to excited, while dominance was related to feeling of control to their emotion. Furthermore, Russell argued that categories emotion can be mapped into two-dimensional valence and arousal space, like in this picture. So, if we know the degree of valence in x-axis and arousals in y-axis, we can obtain the categorical emotion, for example, happy here, according to the Russell. So this is the VAD model, the VA. So what's the problem? In this pilot study, the main problem is to investigate the effect of silent feature to dimensional emotion recognition. Since we assumed previously that silence is related to arousal, we expected that it will influence the prediction of arousal dimensions, performance of arousal prediction. To answer that research question, we developed the following three methodologies. First, we evaluate an acoustic feature set without silent feature and observe the performance. Then, in the second, we add a silent feature to the first previous feature set and again observe the performance. Is there any difference in performance compared to the first step? And third, since threshold factor is important in silence, we evaluate the different threshold factors. If we change the threshold factor from the second step, we use fixed threshold factor and then we change. Is there any difference in performance? So let's move to the first step. First, we evaluate an acoustic feature set to obtain the performance of dimensional emotion recognition. We use GMAP's feature set that is widely used in speech emotion recognition as the baseline. This feature consists of 23 LLDs or low-level descriptors like intensity, alpha ratio, Hamburg index, MFCC, F0, and formants. This is a frame-based processing. So for example, if an utterance divided into 1000 frames, then the feature size will be 1000 multiplied by 23, very big. However, Smith et al. Proposed that using mean and standard deviation of the GMAPs, the small feature set compared to the previous one, lead to the better performance compared to the GMAPs, EGMAPs, and Bag of Audio Words or BAW of GMAPs. We incorporate that finding in this research, so we use mean and STD of GMAPs and we call it as HSF, or high level statistical function. And then in addition, we add a silent feature in different feature set. So this the second feature, the first maybe the Gmaps, and then the second is HSF of Gmaps, and then the third we add silent feature to this HSF. So the third feature is mean, STD, and silence. So what is the silent feature? Silent in this research is defined as the portion of silent frames over total frames. If we define silent frame as NS and total frame as NT, then silent feature can be formulated as NS divided by NT. This silent frame calculation is simpler than counting silent duration, the real silence. So we can see here an utterance is divided into many frames, the moving frames. For each frame, we calculate the RMS energy of signal and then determine if that frame belongs to silence or not by such threshold. For example, using 0.3 or 0.4 of average RMS energy as the threshold. By this method, we can calculate the number of silent frames and total frames, and then divide the number of silent frames over total frames to get the previous experienced silent feature. In this research, we use constant frame length, that is 128 milliseconds, for one frame to represent the silence duration, the minimum silent duration. And this is an example of calculation of silent frames by using different thresholds. As mentioned previously, that threshold factor is important in silence calculation. So here the red lines is the average RMS energy in one utterance here. So in one utterance, for example, there is 120 frames, and this is the average RMS energy. If we set threshold to 0.4, then the frames below this blue line is categorized as silent frames. So to obtain the silent feature, we divide this number of frames by the total frames. If we set the threshold is 0.3, then the number of silent frames below this threshold is counted as silent frames. And again, we divide the number of silent frames over the total frames to obtain the silent feature. If you use the threshold 0.2 and or 0.1, the number of silent frames becomes smaller. So the criteria of threshold will impact on silent feature directly. So let's move to the experiment. We used IOMACAP for the dataset and LSTM for the classifiers. We used all utterance from IOMACAP dataset from University of Southern California, or USG. It is 10,059 turns or utterance with 3 labels. We use the 3 labels: valence, arousal, and dominance. And the original labels is rated by the USG students. The scale of the labels in 5 scale from 1 to 5, but we converted into floating point -1 to 1 following the previous research. And from the classifier, we stacked 3 LSTM layers together, and the last LSTM is flattened and then split into 3 dense layers to represent valence, arousal, and dominance. So the output is the degree of valence, arousal, dominance. For the input, we use different acoustic feature set with and without silence to observe the different performance. So here's the result. We measure our result in CCC, or concordance correlation coefficient. As baseline, we include our previous research using 31 low-level descriptor or acoustic feature sets from Pi audio analysis, and this is the previous result. And using Gmaps acoustic feature set special designed for the affective speech analysis, we improve the performance from the previous result. And on the third method, we use mean and standard deviation of Gmaps, and we got the similar performance, but the size of the feature here is much smaller than Gmaps. And on the fourth method, we add silence to mean and STD, and results here. So here between the third and fourth is only one dimension difference. So we can focus on these two different feature set. Between both, between mean STD and mean STD of silence, we improved all score performance in valence, arousal, and dominance. However, it's clear that the remarkable difference is on arousal. The difference is 0.1, while others are 0.01 here in valence and dominance. So this result suggests that there is effect on addition of silence to this specific acoustic feature, that is silent feature improved the performance of dimensional speech emotion recognition, particularly on arousal dominance. So using different thresholds, we also observe any difference from 0.1 of threshold to 0.4 of threshold. The score of valence and dominance here and here remain similar if we change from 0.1 to 0.2 and 0.3. However, there is again a remarkable difference on arousal. If we change here from 0.1 to 0.2, there is slight improvement, but in 0.3, we obtain a remarkable difference or improvement. So here, the best result is obtained by using 0.3 of threshold. And if we increase the threshold, the performance decreased. So we can exclude the use of 0.4 as threshold. So again, we can see here that the different silent thresholds impact or effect on dimensional speech emotion recognition, on finds arousal and dimension and dominance, and particularly on arousal. So in summary, I would like to conclude that in this pilot study, silent feature by counting silent frames is related to dimensional speech emotion recognition, particularly on arousal dimension. This phenomena may similar to our human emotion perception. And there are two lessons we learned from this research, from this study. First, there is different performance on the use of acoustic feature with and without silence. Our silence feature improved performance of dimensional speech emotion recognition, particularly on arousal. And second, there is a difference on the use of different threshold factor for silence feature calculation. And in this experiment, the best is obtained by using threshold using 0.3. And finally, here is a list of things we want to perform on the future research. And thanks for watching.